So today we're going to start a new topic. That's frequency modulation. So we're getting a bit more modern now, and frequency modulation is still obviously still common. Still a lot of FM broadcast commercial radio stations out there. But these four lectures are going to follow the same pattern as amplitude modulation, in that we're going to start off with looking at modulation, different types of frequency modulation. We're going to look at bandwidth, power, and demodulation. So it's very, very similar to AM, but also very different to AM as well. So let's have a quick look at it. Might have known. Hang on 1 second. This PowerPoint doesn't work. Try the PDF. Okay, that's better. So sorry, the PowerPoint wasn't recognised on this tablet. Some symbols missing were very crucial to this lecture. So, again, coming back to the general carrier wave. So, a signal, a cosine in this case, the amplitude VC, frequency FC, and a phase phi C. And of course, previously we varied VC with the message. So we saw the message sort of impressed onto the carrier wave. We can see it. Now we're keeping VC fixed. We're ignoring phi C. That's zero for what we care for. And we're now going to vary FC with the message. That's a bit more interesting, because now as the amplitude of the message changes, the frequency of the carrier changes. So a very different effect. So because we're varying a parameter inside the brackets of this cosine, so inside the brackets is what we call the angle. So this is known as angle modulation. So there's two types of angle modulation: frequency modulation and phase modulation. As I said in the earlier lectures, we're not going to bother with phase modulation because it never took off. So it's going to focus on frequency modulation. Right. So first thing we're going to look at is actually what is an FM wave. So there's some important things here. Okay, so we're saying that this frequency is changing. So therefore, what we could write is that it's changing, so I've got brackets there, plus, so carrier frequency plus some change in frequency. Now what this means is that, so FC is what we call the unmodulated carrier frequency. So that's sort of like, that's where everything's centred at. And then the FC will either increase or decrease depending on if the voltage is positive or negative. So this obviously, this here is we've got to connect this with the message. So because the message is always changing, that frequency is always changing. So what we do, we refer to it, this FC plus delta F, as the instantaneous frequency. And write it like that. So now, Fi is not fixed, it's continually changing with the message. So now, what we've got, if we've got an instantaneous frequency, then we have an instantaneous angle. So so everything in here is called the angle. So we denote it with this Greek letter, And I forgot what it's called, that Greek letter. Anyone know that one? Is it, which one? Phi, is it? Yeah, it is phi, isn't it? Yeah, that's right. Yes, phi. Yeah, just went blank for a minute there. So, we've got an instantaneous angle. What we're going to do now is connect this angle with the message. So, I've got last, I've got last year's notes on here, but they're still relevant. Save me writing them again. Okay.
Sorry.
Yeah.
Could you put that projector thing down a bit? That one that's stuck in front of the screen.
Oh yes, this thing, yeah. Is this lectern in the way as well? No. Not bothering anyone? Okay, we'll leave that where it is. Okay. Right, so we have phi I is equal to 2 pi f I t. Okay, see that's pretty clear. And we're going to differentiate both sides. So we're differentiating with respect to time. So we treat 2 pi fi as the constant. So obviously differentiating that will just be 2 pi fi. Okay. So therefore, fi is 1 over 2 pi psi I by dt. So we have this relationship between instantaneous frequency and the rate of change of angle. Okay. So now we come to the sort of the most important step, and that is connecting all this with the message. So we've got an expression for fi. That's going to play a part. This is going to play a part a bit later. But we also want to relate fi to the message. So fi needs to change with the message amplitude. So this is the most important step in understanding frequency modulation. That's why I've underlined it. So instantaneous frequency is a carrier frequency, unmodulated carrier frequency. That's constant. Right, this term, delta fc times the cosine 2 pi fm. So we're going to treat the message as a single frequency of fm, just like we did with the AM analysis. Keeps everything simple. And we're saying, obviously, that's a cosine. So the cosine will vary between +1 and -1. But we're multiplying it by this delta fc, which we're going to call peak deviation. So now this term is going to vary between plus delta fc and minus delta fc. Let me just write that down. So we're saying that fi, in addition to being equal to this, 1 over 2 pi phi by dt, is also equal to the unmodulated carrier plus a change in the message amplitude, which is translated to a change in frequency. So we're going to define peak deviation, and then we're going to put our message in. So you can see that we're putting a limit on fi in both directions, a lower and upper limit. So in the middle is fc, that's the middle frequency. It can go up to, well, fi can go up to fc plus delta fc. That's the maximum value from this term. Yeah, because delta, so this term can vary between plus delta fc and minus delta fc. So we've got fc plus delta fc is a maximum instantaneous frequency, and fc minus delta fc is the minimum instantaneous frequency. So we put a limit we put limits on the instantaneous frequency. So the carrier cannot go above Fc plus delta Fc and can't go below Fc minus delta Fc. Okay. So we have to remember that all of this, again, is equal to 1 over 2 pi d phi I by dt. Right, so now we're going to do the clever bit. What we're going to say is d phi I by dt is equal to 2 pi fc, so I'm multiplying both sides by 2 pi fc. I'm multiplying both sides by 2 pi, sorry. Okay, and now I'm going to integrate both sides so that I get an expression for instantaneous angle. Now, thankfully, the integration is pretty simple. We've got a constant term here. So if I integrate a constant, I get the constant times t. So that's 2 pi fct. And then I've got a cosine term. So we know how to integrate cosine. Becomes a sine. And we also have to divide by the derivative of what's inside the brackets. So integrate this, I get the sine term, sine of 2 pi fmt, and I've got to divide by 2 pi fm. Okay, so that's basic A-level calculus. Okay, just integrating the cosine. So we get, so 2 pi delta f will stay the same. So fc. Sorry. The cos becomes a sine. And then we have to divide by 2 pi f. So, obviously, 2 pi's will cancel. And all we have now is one last step. So remember, if we just go back a few points, the carrier, the actual FM carrier was defined by Vc times cos of the instantaneous angle. Now we have an expression for instantaneous angle. We're just going to substitute it back into here. There we go. That is the expression for an FM wave. And the first thing you notice is it's a lot less pleasant than the AM wave equation, which was nice. Could deal with that. AM wave equation, all I had to do was apply a simple trigonometric identity. I could see what frequencies were present in the AM signal. This, however, is a different proposition because I've got a cosine of a sine. You don't see that every day. Now that's just a case where we had a message with a single frequency. Imagine if we had a very complicated message, this would be a horrendous expression. So we're keeping it very simple. We still have an expression that really doesn't really tell us much. We can plot it, and you can do that yourselves, plot that, put different values in, and you can see the wave. But I don't know what frequencies are in that wave. I don't know if it's like AM. Has it got a carrier component and a pair of sidebands? Or is it something different? You can't tell just by looking at that. So what we have to do is use another mathematical technique, and thankfully people have already done this for us, so we're just going to use it. We don't have to understand it. We're going to look at something called Bessel functions. Okay. Now, one thing that we can get from the FM equation is a parameter called modulation index. And in a similar way that we have modulation depth in AM, changing modulation depth gave us different kinds of AM waves. Changing the modulation index gives us different types of FM waves. Has a slightly different equation though. Whereas modulation depth was the ratio of two voltages, message voltage and the DC voltage, this is the ratio of two frequencies. The peak deviation, the maximum amount that the carrier frequency can change by, divided by the message frequency. So again, it has no units, just like modulation depth, because it's frequency over frequency. But different values will give us different kinds of AM waves. FM waves, sorry. Right, so the key thing here is transforming the FM equation into something that is a bit more friendly and that we can actually see what's going on. These things. Right. So the transformation we're going to use is a Bessel series. You're going to see a lot of series in this degree. A bit later on you're going to see, well, you've already seen Fourier series in maths, I believe, in stage 1, briefly. A Bessel series, there are other series as well. We're going to look at Z transforms, which is like again, is a series, is another series, basically. And this is a Bessel series, and what it does, it allows us to transform functions that look like this into an infinite sum of cosines with different frequencies and amplitudes. And this Jn beta is called the Bessel value, and basically gives us the value of a particular frequency component. Now, unlike AM, the sidebands are changing depending on the value of the modulation index. And also, there's more than one pair of sidebands. In fact, according to this equation, there are an infinite pair of sidebands in FM. Mathematically, that is true. Now, practically, that's not feasible. Can't have that infinite bandwidth signal. So what we'll actually see is that most of these sidebands can be filtered out because they're trivial. Very, very small amount of power in them. Filtering them out doesn't make any difference to the signal. We're going to look at that a bit later. But if you expand this FM expression as a Bessel series, you can see this is for the first two pairs of sidebands. You've got a carrier component, so just like AM, a carrier component in the middle. This is the unmodulated carrier frequency, and it has an amplitude equal to Vc, which is the amplitude of the carrier wave, which is fixed, because remember amplitude doesn't change, it's frequency. Vc is fixed, but it's multiplied by these j's. So we've got the 0th order Bessel function as a function of modulation index. So depending on what beta is, that's going to be a different amplitude. And then we've got first pair of sidebands. So up to this point, the first line looks just like AM. Look, you've got an upper sideband, Fc plus Fm, and a lower sideband, Fc minus Fm. But now, of course, you've got a second pair of sidebands with their own amplitudes, and a third set and a fourth set, etc. So it's a little bit more complicated than AM. So when we actually look at the spectrum, this is a very generic spectrum, and what we find is we're going to have lots and lots of frequency components, all and symmetrical, so the sidebands all have the same amplitudes. Each pair has a same amplitude. But what's happening is that if we start with a very small value of beta, in fact beta is 0, that's the smallest we can have, we actually have no modulation, and we have a single carrier frequency, and that's it. As we increase beta, more sidebands rise, they come up. Now, as we increase beta, more sidebands come up, but the ones that are already there will start to come down. And the reason for this is because the FM signal has a total power, and only the frequency changes, not the amplitude. So the power is fixed. So with AM, the power changed when you modulated the carrier because you added sidebands. But this one doesn't. The power is fixed because the carrier amplitude is fixed. So therefore, when new sidebands come up, that will increase the power, but to keep it fixed, other sidebands have to go down. So mathematically have to go down. So that total power is always the same. So as we introduce more sidebands, existing sidebands go down. Keeps the power fixed. Something you're going to see when you do the FM lab. Right, so why is that the case? So what we've got here is a plot of different Bessel functions. And each line corresponds to a frequency component, a pair of sidebands. So each line is a pair of sidebands. So the number here is beta, so the modulation index. At beta is 0, we've only got one value. We've got a single Bessel function and has an amplitude of 1. And what that means is there's only one frequency, because beta is 0, it's unmodulated, it's just the cosine at a frequency fc, that's it, there's no message. And as we increase beta, let's go to beta is 1, now the carrier component reduces, but then we have one set of sidebands, they come up, and then we've got another set of sidebands and a third set of sidebands. So you can see the carriers come down, that's reduced the power of the signal, but that now we've got some sidebands coming up, which is then sort of compensated for that loss. So the power is still the same as it was before. So the same power as it was here. So as we keep increasing beta, more and more sidebands rise. We get an interesting case. In fact, there's more than one interesting case, but the first interesting case is when the modulation index is 2.4. Because here, at 2.4, the carrier component is 0. So that central frequency at Fc is 0. So it looks a bit like a double sideband AM suppressed carrier. The component at Fc is 0. But the difference is that we've got other sidebands now where all the power is. So there's no power in the carrier components, all the power is in the sidebands in that case. That's something that you're going to actually find when you do the FM lab. You're actually going to increase beta and see the sidebands come up and keep an eye on this sideband until it gets to the noise, and then record what amplitude that happens at, and then calculate your beta. Is that beta, is it close to 2.4? It's actually one of the tasks on the FM lab. So it's all very relevant. Happens again about 5.5 as well. You get another case where the carrier is 0. Now, actually determining the values, that's what we need to do next. So, thankfully, there's no maths involved. We haven't got to calculate Bessel values. I wouldn't wish that on you. We have Bessel tables, Bessel function tables, and they're much larger than this. This is just a very small piece of a large Bessel table. And basically, we read them like this. So first of all, we have to calculate our modulation index. And then once we've got that, we know which column to look at. So in the brackets here, this is your value of beta. Selected values of beta. So we haven't got all of them, but when I ask a question about this, it won't be. It'll be one of these values of beta. And then here in this column is the frequency component. So 0 corresponds to the carrier component in the middle. 1 is the first set of sidebands. Second set, we've gone down to 8th set. Obviously, this goes down to infinity mathematically, but we're not going to focus on that. So when beta is 0, there's no modulation. So therefore, we just have a carrier component and nothing else. And then a slightly larger value of beta, we can see the carrier component comes down a little bit, and we have a few sets of sidebands coming up, and everything below is 0. So you can see that as we increase beta, more sidebands appear, and they will do so if we carried on. And you can see the case where sometimes the value is negative. So in that case, we actually take the absolute value, because that's what the scope does. When you set it to spectrum analyzer mode, it doesn't show you negative values, it takes the absolute value. So this will be plus 0.0483, plus 0.26. Okay, so don't worry about negative values. Right, so a couple of examples, and then we'll draw one ourselves, because obviously that's the best way to understand this. So beta is 0, just a single carrier component at VC. That's as we expect. Beta is 2.4, the special case where the carrier component is 0. You can see no carrier component, but we've got these values. So VC is something we decide what that is, but obviously whatever it is, half of VC is at this sideband, half of VC is this sideband, etc. So different proportions of VC are spread over the spectrum. So let's actually do one. Well, actually, no, before we do one, I've got to talk about band-limited signals first, because obviously we have to know when to stop. I said there's infinite sidebands. That can't be the case. We'd have to know when to stop. So we're going to band limit our FM signals. And what that means is we're going to find which components we don't need and filter them out, so that now we have a finite bandwidth. Because in reality, we only have a fixed bandwidth we can use, which we've bought, and we can't exceed the bandwidth because we get fined. So if our spectrum is very wide, so here for example is a typical spectrum. If the bandwidth exceeds this bandwidth, then we're leaking over into something else and causing interference with that person's bandwidth, and that's not allowed. So we need to filter out the sidebands that are greater than the bandwidth. Now, as it turns out, that's not a difficult problem. What we're going to do is just find all cases where the Bessel value is less than 0.01. So we go in our Bessel table and we find, go down until we find a value that is less than 0.01, and then we say that is an insignificant sideband, we're not going to use it, we'll ignore it. And everything below that will also be insignificant because it gets smaller and smaller as you go down the rows in that table. So we're only keeping values that are greater than or equal to 0.01, which is, or the equivalent, we're only keeping components that are 1% of the carrier amplitude and no less. So at least 1%. So in this example here, for beta is 1, we keep going down. So 0.0196, that is slightly greater than 0.01. So we keep that. But then the next one, 0.0025. That is less than 0.01, so it's insignificant. And obviously everything below that will also be insignificant. So we stop there. We just say, right, this FM signal has 3 pairs of sidebands. That's it. So it has a finite bandwidth. So let's do an example. So we'll need a Bessel table. Okay, let's pick any example. Let's do the one in the middle here, 1.5. Okay, so can anyone tell me how many significant sidebands, how many pairs of significant sidebands that signal has? A modulation index of 1.5. How many significant sidebands does it have? 2? 4? Yeah. 0.0117 is slightly greater than 0.01. We keep that one. 0.0017 is obviously less. So everything below that we ignore. So we stop at n equals 4. So straight away, our spectrum has got a carrier component and 4 pairs of sidebands. We know that much. The next thing is, what amplitudes are these sidebands? So for that, we're going to do an example. And so I'm just going to write down the Bessel values. Okay, so I'm going to have to sort of flip between the two just to remember the numbers. So 0.5118. 0.5579. 232. Is that the next one? 0.0609. And then 0.0117. Okay, so we've got our Bessel values. Now we need some more values. So what I'm going to give you, I'm going to give you a carrier amplitude of 10 volts, an unmodulated carrier frequency of 1 megahertz, and we'll have a message of 1 kilohertz. Okay, so this is just that's a simple example. Those are any values we need to sketch the spectrum. So what we can do is introduce another column for the amplitude of each component. So that's going to be VC times the Bessel value. In this case, I've made it easy because we just multiply all the Bessel values by 10. So there we go. Those are the amplitudes of the different components. Now we need to know where they go. Which frequencies do they go? So we know we've got, the first one is FC, and that's 1 megahertz. And then the next one, we've got a pair of sidebands. So that's going to be FC plus FM and FC minus FM. And then the next set will be FC plus 2 FM and FC minus 2 FM, and then FC plus 3 FM, FC minus 3 FM, and then FC plus 4 FM, FC minus 4 FM. Okay, now obviously we can put numbers to these frequencies because we know the values. We'll do that on the graph. when we draw it. So now everything we need. Let's just put a set of axes for frequency spectrum, and we'll express the frequency spectrum in terms of megahertz, the frequency in terms of megahertz. Okay, so let's put the center frequency in first, FC. And FC is, of course, 1 megahertz. And then we've got FC plus FM. So that's 1 megahertz plus 1 kilohertz. So that's going to be 1.001 megahertz. Then we're going to have FC minus FM, which will be 0.999 megahertz, 999 kilohertz. And we'll just keep doing that. So it's going to be 1.002. .998 megahertz, and so on. Okay, raise that up so you can see that. Okay, so it's a bit cramped. Hopefully you can see that. So we've got carrier components, 4 pairs of sidebands. So now we're just going to put in the amplitudes of those components. So the first one at 1 megahertz is 5.118. And then the second set of the first set of sidebands is actually slightly greater. It's 5.579. And then the second set of sidebands come down a bit more significantly, so 2.32. And then the next two are quite small. So we've got 0.609 for the third set of sidebands, and 0.117 for the fourth set of sidebands. So there is our frequency spectrum of that particular FM wave. So you can see a little bit more challenging than sketching AM frequency spectrums, but once you know your value of beta and you have a Bessel table in front of you, you're then able to sketch the frequency spectrum. Okay, are there any questions about that? Any questions at all about FM in general? Yeah?
Is there a reason why we define the AM modulation depth as the ratio of the message amplitude to the carrier, whereas here it's kind of flipped? Is it more convenient to do it one way or the other?
Well, no. Basically, it all comes from the equation. Let me just, where did I put it? Here. Here we go. So basically, it comes from here. Yeah. So if you remember, the AM wave had a similar equation. Well, not similar to this, but there was a VM over VDC term in the AM equation. you probably forgot this now, but we actually took the AM equation, we took a factor of VDC outside, so that we could express the AM equation so that it had the ratio VM over VDC inside. And this has a similar ratio, so this is what we vary. So that's where it comes from, basically, modulation depth. So you can replace delta FC over FM with beta in this equation. Okay. Right, so now that we have a band-limited FM signal, that means we can measure the bandwidth, a very straightforward thing to do. In this particular example, which I think was beta is 1, we don't need to know actually the amplitudes of the components, we just need to know what frequencies are present if you want to measure the bandwidth. So obviously it's the highest frequency minus the lowest frequency. So FC plus 3FM minus FC minus 3FM. So obviously FCs cancel out, and we're left with 3FM minus 3FM, 6FM. So actually, the carrier frequency has no effect on the bandwidth at all. It just shifts the spectrum, that's all it does. It doesn't change the bandwidth of it. It only depends on FM. And the bandwidth itself as well also depends on beta. So as long as we know beta, from the Bessel table we can actually calculate the bandwidth of the spectrum without even sketching it, because we just know what frequencies are present. So if we look at our example, can anyone tell me what the significant bandwidth is of that signal? 8 kilohertz. Yep. So the bandwidth is going to be 1.004 megahertz minus 0.996 megahertz. Calculate that, you will get 8 kilohertz. Okay, so in this case, which is the same as 8 times the message frequency, because the message frequency was 1 kilohertz in this example. So significant bandwidth is going to increase as beta increases. So beta is 1, it was 6 times FM. This is beta is 1.5, it's 8 FM. And if you keep going, if you actually went to beta equals 10, it's 28 times FM. Okay? I'm actually going to ask you to find beta is 10 in the FM experiment. So that'll be interesting. It's a nice big wideband FM signal. Okay, all happy with that? Right. And here we are. If you actually look at this table, quite an interesting table, showing us how the bandwidth varies with increasing modulation index. 0.1, very small value of beta. We have just two sidebands, or one pair of sidebands, and the bandwidth is 2 times FM. Actually, that's the same bandwidth as AM, double sideband AM. That was 2 FM as well. And see, increasing it increases the number of sidebands. So as I said here, you've got 14 pairs of sidebands when beta is 10. So bandwidth 28 times the message frequency. Now, there is another measure of bandwidth, which is an approximation. It's not actually accurate, but it sort of gives you a lower bound. If you needed to quickly work out the bandwidth, just roughly, you can use Carson's rule. Carson's rule is based on the assumption that within this bandwidth, 98% of the total power, 98% of the FM signal is in that bandwidth. It's worked on that assumption. So in this case, you don't even need Bessel tables to calculate Carson's bandwidth. all you need to know is peak deviation and the message frequency. So if we were to go back to our example, so as a reminder, where's it gone? Here we are. So we've got FM is 1 kilohertz. We haven't got delta FC, but we can calculate delta FC because we know that modulation index is delta FC over FM. So therefore, peak deviation beta times message frequency. So what is the peak deviation of this FM signal? Not quite. Not quite. In fact, no, actually that's 10 times, that's nearly 10 times higher than the number I've got. What value is beta in this example? 1.5. 1.5. And what value is message frequency? 1 kilohertz. There we go. So it's 1.5 kilohertz. So that means that the carrier frequency is centered at 1 megahertz and it won't go higher than 1 megahertz plus 1.5 kilohertz. It won't go lower than 1.5 minus, sorry, 1 megahertz minus 1.5 kilohertz in the time domain. Now that's not what we want. We want this because we want to calculate Carson's bandwidth. So if we calculate that, which was approximately 2 times delta FC plus FM, then we get 2 times 1.5 times 10 to the 3 plus 10 to the 3, and therefore that's, if I'm correct, that is 5 kilohertz. Yeah. So as you can see, it's lower than the actual bandwidth, which is 8 kilohertz. And the reason is because of the assumption that 98% of the power is in that 5 kilohertz. But 99.999% of the power is in that 8 kilohertz. Well, then you couldn't have if you made that assumption, then Carson's bandwidth wouldn't have this simple equation. So this is a general rule of thumb for engineers who don't have a Bessel table on them. They can just get a rough idea of what the bandwidth is by using Carson's rule. Okay, so I think that's probably a good place to stop, since it's nearly 5 to. I think the next thing we're looking at so next time what we're going to look at is power in FM signal. Those of you who've got your labs today, please be there at 2 o'clock in the electronics lab. Is anyone here who's doing the lab today? Okay, that's a lot of you. That's good to see. Great. So I look forward to seeing you all there at 2 o'clock. And the rest of you I'll see tomorrow at 9 o'clock in the Herschel building. Thank you very much. Hello.
I wasn't here last week. I'm not sure if you received an email from me or not.
What's your name?
George Kulis.
I think I did.
I think I sent one, but my emails have been quite dodgy with things getting trapped in the outbox. Basically, I wasn't here last week because I had corona. I've recovered from it now and everything.
Well, I've got my mask on.
Yeah, I've tested.
I'm advisor. I'm double
But
protected.
is there a time that I could come in maybe just to ask one question? Because I've got I've written down some questions, but I've
Cool,
never.
Yeah, the wood actually. You call in, are you free on Friday?
Yeah, Friday. Ooh, actually, maybe not. I think it's quite packed there.
I don't mind. I mean, we can have a virtual meeting if you like in the evening.
Yeah, that's fine.
Shall we do that?
Yes, please.
A Teams meeting. Is that okay?
Cool.
Yeah.
So shall I send you an email just to confirm it?
Yeah, send me an email because I tend to forget.
Yeah, okay.
Usually what happens is I walk to my office and then someone of the students will come up to me and then what you've said has been overwritten. Yeah, send me an email to remind me, then I'll send you a Teams invitation. Any particular day?
Teams is fine, as long as I don't have a lecture, it's fine.
Yeah. I mean, do you want to do it like after 5 o'clock?
Yeah,
okay. So, well, 5 o'clock I'm in the lab, so tomorrow?
Tomorrow, perfect.
Yeah, we've got a lecture. Oh, 4 to... No, Wednesday 9 to 11. Yeah, tomorrow I'll call you after 5 o'clock.
Okay, thank you very much. I'll send you an email just...
Yeah, send me an email. Okay, thanks very much.
Thank you very much.
I'm just wondering about the practical. Of course, last year the drawing class was given all all the safety stuff.
Yeah.
So I'm just thinking how much we actually need.
None.
Oh.
I'm not downplaying the safety aspect, but electronics is sort of the cleanest, safest.
Yeah, I was going to say because if we turn the
it's low voltages. You're not going to drop anything heavy on our foot. You're not going to get shocked. There's no danger of being infected with acids or anything like that. So you don't need to bring any of your PPE.
I was just checking just in
It's a
case
good
it
point.
got there.
Someone else asked me that yesterday, and I've never thought about it before because electronic engineers don't need any protective equipment, well, apart from now. Yeah. So just bring yourself. That'll be enough. Okay. Hello.
So you know how we have the frequency spectrum.
Yeah.
We don't really understand how those visually translate into the waves.
Well, it's the same as AM, really. I mean, each one of those lines is a cosine, right? So and you're adding them all together. So you've got a cosine of the frequency of 0.996 megahertz, of an amplitude 0.117. So add all those cosines together, and you'll get the FM wave.
Oh, okay.
Yeah, that's what it is basically. Yeah. So it's just like AM, where you add the sidebands and the carrier code together, you get that AM shape. Yeah, you'll get the FM shape. So it'll look like right at the beginning here. It'll look like that.
Yeah.
And all together. Yeah. Okay. No problem.
So what does it mean if the frequency spectrum, if it's like small or large? So how does it represent on the graph?
Oh, well, so here, you've got low frequency here.
Okay, so
That corresponds to
the
a low
frequency-
amplitude
Oh, the
of the
frequency is
message.
slow, yes.
And the higher frequencies are the high
So
amplitudes.
it's, okay.
Yeah, this is, I think this is actually FFK, which is, I think it's just a square wave.
Digital.
I think it is, yeah. I think I just wanted to find a waveform that exaggerated the changes in frequency. Yeah. So that's basically it, yeah. So higher frequencies mean higher message values, voltages, and low frequencies are low message voltages. So that's the connection between the two.
All right.
Yeah.
I wanted to ask about the lab today. Do we have to bring our goggles?
No. It's a new thing. This is because you've done this stage one the first time, and obviously civil and mechanical are a bit more dangerous. Now we are very safe and very clean. Just bring your mask. That's basically what you need.
All right, perfect.
Yeah.
All right,
Okay.
thanks a lot.
No
Thank you.
problem.
See you
later.
this afternoon.
Yeah. See you later. Right, bye.
Oh yeah, so that one is like all videos. All? Yeah, so like all, where it says lecture links, they're all videos that she gets you to do. And the first lecture. Yeah, so that was last week's, and